Alrighty, y'all. Today I'm taking a look at question 5 for homework 2 and question 6 because I decided to lump them together. So for question 5, we're trying to find the electric field at the surface of a ball. So if we have our ball here as our charge, we're going to just put like a little tiny Gaussian surface around that. That's what we're going to use because it's going to have, since it's a sphere, it's going to have spherical symmetry. Lovely. So that means we get to use the equation that our electric field is equal to our Q enclosed over 4 pi epsilon naught r squared for our spherical symmetry. And now we just get the joy of finding our Q enclosed. Since we're at the surface of the ball, it's going to be the full, since it's going to be 1 times 10 to the negative 9th, and that's in coulombs per meter cubed. We're just looking for coulombs, so we're going to multiply by the meters cubed, which is just going to be the volume of the sphere. So that times our volume of the sphere, which is going to be 4/3 pi times our radius, 0.02 cubed. Now we're just going to take all this, yeet it right on there, because that's going to give us our Q enclosed. So I'm going to do our electric field is equal to 1 times 10 to the negative 9th times 4/3 pi times 0.02 cubed. And I write it out like this so that I can have 4 pi epsilon naught r squared on the inside. And we can go zoop, cancel out the 4, cancel out the pi. Oh, this r, since we're at the surface of the ball from this center, our r in this bottom bit is just going to be the r for our actual sphere as well, right? So squared, that's going to go away. This is going to just become to the first power. So all this canceling just means less math that you have to punch into your calculator at the end. 10 to the negative 9th times 0.02 all divided by, and I'm moving this 3 down to the bottom as well because I can, and that's 3 times epsilon naught. You plug this in with, of course, epsilon naught equals 8.85 times 10 to the negative 12th, and it's going to give you your answer for the electric field at the surface of the ball. Now on to question 6, and we're looking for the velocity when a charge is infinitely far away. So since we're looking for velocity, it's a pretty fun cue-in that we're going to be using our conservation of energy. So that's going to be our potential energy initial plus our KE initial is going to equal our potential energy final plus our KE final, kinetic energy final. So it says that is released from rest. There it is. So our initial kinetic energy is going to be 0. And then it says when it's infinitely far away from the helium nucleus, if it's infinitely far away, that means that the potential energy, the electric potential energy is going to be 0. If it's infinitely far away, it's going to have an infinitely small potential energy. So that leaves us with our initial potential energy is going to equal to our final kinetic energy, right? And our initial potential energy, that's going to be our KE, Q1, Q2 over R. And of course, then we get our kinetic energy, just 1/2 mv squared. Now we can plug some things in. So we get KE times Q1 is, we'll just say, is the helium nucleus. So that's going to be plus 2e, so that's going to be 2 times 1.602 times 10 to the negative 19th. Almost forgot that for a second. And then that's going to be multiplied by just the proton, so that's going to be 1.602 times 10 to the negative 19th. That, move that over there, is going to be divided by the R, the initial R, which is 1 nanometer, so that's just going to be 10 to the negative 9th, That's going to equal 1/2 times the mass that it's moving, it's in kilograms already, so we don't have to convert that, 1.67 times 10 to the negative 27 times our v squared. Now, if we solve this monstrosity here for v, we're going to get Ke. I'm just going to factor out this 2, so it can be 1.602 times 10 to the negative 19th squared, all over 10 to the negative 9th. And that's if we're multiplying by 2 to get rid of that. Then we're going to have another 2 here. And we're going to be dividing by this to get rid of it. So that's going to be in the denominator with our 10 to the negative 9th. It's going to be 1.67 times 10 to the negative 27. And that's going to equal our v squared. But then we're just going to take the square root, get rid of that. That's going to give us our final velocity when it's infinitely far away from the point, because if we plug all that into your calculator, of course using Ke equals 8.99 times 10 to the 9th, and that's going to give you your answer for question 6. All right, well, thank you all so much for watching. I hope this one was helpful. Let me know if you have any questions or if you have any other problems that you'd like to see worked out, and I will do my best to explain them because I guess Sydney explains stuff.